Good morning, ladies and gentlemen. So today we are going to start a new unit, Unit 11. And this unit is called Solution Chemistry. So very quickly, what is a solution? A solution, right here in our definition, is pretty much any two substances or more mixed and dissolved together. So we'll talk about what all of these words mean, but we're going to have two substances, be it like salt and water, right, mixed together, or sugar and water mixed together. And other solutions would be chocolate milk. Air is also a solution. It's made up of nitrogen, oxygen, carbon dioxide, water vapor. All of that is a solution. A brass ring, maybe like my gold ring, believe it or not, this gold ring is a solution. It's made up of gold, silver, molybdenum. It's made up of all sorts of different stuff. And then maybe Mr. Edwards' trumpet that you could probably hear playing in the background. All of those things, those are solutions. This is just a solution that's solidified, right? Steel is a makeup of usually iron mixed with carbon, all right, in different proportions. So that's what we're going to be talking about. We're going to be talking about solutions today. Now, let's take a look at some vocabulary. This vocabulary, we're going to move through it. All right. So, a solvent, ladies and gentlemen. A solvent is a substance that dissolves other substances. So, the one thing that I think you should memorize is that water is called the universal solvent, because pretty much everything that we come in contact with, except for many things, but a lot of things we come in contact with, are going to dissolve in water. You think about the ocean, right? The ocean, you taste it and it's super salty. There are so many different dissolved pieces in the ocean water, it's not even funny. And that's because most things on the planet, besides like oils and rocks and stuff like that, will dissolve in the ocean. All right, so let's move on. So a solvent is something that dissolves other stuff. The other part of that is going to be the solute. The solute is the substance that is dissolved in other substances. For example, if you have a container of water and you have a bunch of salt and you put the salt into the water, the salt just it disappears. The salt is not in the water. It's kind of in the water, which we're going to get to what that means exactly. So a solute would be like the salt, and the solvent would be the water. So let's move on. All right, so we just covered these two things. We just covered what a solvent was and a solute. And now that's going to help us solidify this, this idea. You know what? And then I did just jump into my lecture without starting you guys off. I highly suggest that you take out your notes and you take notes on all of this stuff, because I'm just going to move through it quickly. And if you want to stop, you can stop the video, write notes, because you're going to have to be responsible for this information. So now we're going to talk about what is a true solution. All right. So a true solution, ladies and gentlemen, is a homogeneous or homogeneous mixture between a solute and a solvent. The solvent dissolves the solute to make a solution. So we have the water again, and I'm going to go through this example a lot. We have the water, which is going to be the solvent. And then we're going to take the salt. Here's our salt. This is the solute, and we're going to put the salt into the water, and the solute is going to dissolve to make the solution. All right, and we're going to talk about those solutions right now. So let's talk about this word homogeneous. All right, so the word homogeneous means the same throughout. All right, so what does the same throughout or uniform throughout mean? What it means is that if you have a solution like this Windex, which we use for cleaning windows, let's just say that you take a spoon and you dip down into the Windex. Will you get a better solution if you take the Windex at the top or if you take the Windex at the bottom? Or are you going to get the same no matter where you take a scoop? Hopefully you said you're going to get the same no matter where you take a scoop. And the same thing goes for coffee. Coffee is homogeneous because wherever you take a scoop of that coffee, you take a little spoonful of coffee, you don't have to say, oh, I want to take the first spoonful, because all that coffee is the same. And this gold ring is the same throughout. So some examples we just talked about were coffee, Windex, and a gold wedding ring. People can argue about whether or not air is homogeneous or not. And when we have our class discussion, I'm going to ask you whether you think air is homogeneous. Where do you think air is the same throughout the whole thing? Okay. So now let's talk about things that are not homogeneous, right? And examples that are not homogeneous, ladies and gentlemen, are going to be things like muddy water. So if we have muddy water, if you take a scoop of the mud right there and a scoop of the mud right there, you're probably going to get something different, and you can see it because these particles are sinking. So if you scoop up here at the top and you scoop down here at the bottom, you're going to get different stuff. This one might have more particulate matter and this one might be less. And you can really see it if you take a scoop there and a scoop there. And a chocolate chip cookie is the same. Let's take say you take a bite of a chocolate chip cookie right here. Is it exactly the same as if you took that same bite right here? Nope, because here you got one chocolate chip and there you got your 4 chocolate chips. So we call these heterogeneous. I didn't write the word heterogeneous, but heterogeneous. But that means not the same throughout. And you can really see it with this salad. Depending on where you scoop this salad, you're going to get something different every single time. So homogeneous means the same throughout, and heterogeneous means in different places. Most of the things we talk about in class are going to be homogeneous solutions. That's what we're going to be working with the most. Okay. So, yeah. All right. So let's talk about some units that we have in chemistry. So the unit that we're going to be using the most, the metric unit that we're going to use the most in this solutions chemistry unit is going to be the liter, right? So liter is how we measure volume, and volume is 3-dimensional. A lot of you kind of understand 3-dimensional, like there's a box, but then I can make this amazing because my drawing skills are phenomenal. We can make this 3-dimensional box. So you guys have probably seen these little hydro flasks. I'm not selling hydro flasks. Let me block that out so you guys don't think I'm getting any money from them. This 1 liter, this container is about 1 liter. These containers here, these Coke bottles and Sprite bottles, these are called 2-liter containers. They contain 2 liters of stuff. And we buy them as liters and we don't even think twice about it. Now, a half of a gallon is about 2 liters. So if you need to try to visualize how much things are, that's 2 liters. A gallon is about 4 liters. So you'd be able to pour 4 of these hydro flasks into a gallon container. So this is about 4 liters of material. All right. So that's the unit called volume, and we measure it in liters. So what does it mean to dissolve? Well, to dissolve means to pass into a solution. Usually, it doesn't have to be solid. It can be gases as well. But usually means we use it as you take solid like salt and you dissolve, or you put that solid into water and it kind of disappears. It's still in there, but we just can't see it usually. All right, sometimes they're colored, but dissolving means when you put salt or sugar in water and that salt passes into the water or goes into the water. All right. So that's what dissolve means. So now we're going to talk about the word soluble. Soluble is the ability to dissolve. This is one of the words we're going to be using a lot. It's called soluble. And soluble means the salt or whatever can dissolve in the water. For example, this is a cup of salt water. The salt has been dissolved in the water. And this is a picture of sugar water. We've taken solid sugar and put that into the cup. Now, if these two cups look exactly the same, that's good. They are the same picture, but this is what the difference is between salt water and sugar water. You can't see the difference, okay? So that would be soluble. So we just talked about what soluble means, and that's the ability to dissolve. And in our class, we're really just dissolving in water, especially this year. So soluble is the ability to dissolve in water. Insoluble means not being able to dissolve in water, okay? And one of the things that you can kind of get your idea around is when you mix oil and water. Oil does not mix very well with water. They don't dissolve in each other. They actually form a layer and they don't dissolve, okay? Same thing with this muddy water. These little particles of sand, they don't dissolve. They go down on the bottom of this container and will sink to the bottom, and they'll form what's called a precipitate, which we're going to talk to probably in about 30 seconds. But that is what insoluble is. And you will work with this word a lot. So we're going to have lots of insoluble solutions, and we're going to have a lot of soluble solutions. All right. So let's take a look at what a precipitate is. All right. Now, we're going to do a lab in about probably 3 days, 3 class periods, where we're going to be working with these things called precipitates. Basically, what a precipitate is it's a solid that forms in solution. This one right here, okay, this is lead iodide. And you can see that the solution over here is clear. It started off a clear solution, and then we're dripping in a clear solution as well. And when we click in this clear solution and another clear solution, it forms a solid, okay? A precipitate is a solid, and that comes out of solution. You can see all of these. These are some of the precipitates we'll be forming in class. So you'd have the solution, right? And then in the solution, you'd have these solids that are hanging in there. And then the precipitate, over a period of time, would sink to the bottom. Now, we do have some tricks that help us speed that process up. And I'll show you that once we get to it in class. But this word is a precipitate. And you'll see Mr. Pepik abbreviate precipitate with the letters PPT for precipitate. All right, so let's get to the last big thing that comes with this unit, all right? And that's gonna be the word molarity. We still have more things to do, but the biggest part of this unit eventually is gonna be molarity. Molarity is a fancy word in chemistry to talk about concentration of something. And I'm not talking about focusing and like really trying to think. I'm talking about how concentrated something is. So it's a mathematical way of describing concentration, which I'll explain to you in a second. The unit for molarity, okay, it's the abbreviation is a capital M, not a small m. And the units are the number of moles of solute, which would be like the salt, for every 1 liter of solution, which the solution in this case would be the salt water. And so the unit would be given as moles per liter. So if I put in 1 mole of salt, NaCl, into a container that filled up to 1 liter, if I put that in there, then I would have a salt water solution. And since 1 mole went in, then I would have 1 mole of salt in 1 liter of NaCl or salt, SOLN, abbreviation for solution. Okay, so that's what that is. Where we'll be working with that is right here. So you can see right here, this is molarity. I give you the unit on this table. It's the number of moles per liter, ladies and gentlemen. The number of moles per liter, right, of solution. And that allows us to convert from moles into liters. And that's liters of solution, all of these key words. But it's going to be a couple days before we do that. I just wanted to introduce that word to you because I'm going to start using this word. Very quickly, what does it mean to be concentration? Well, let's say that we make lemonade. So we have lemonade, and you sit there and you're just like, oh man, it's way too sugary. What do you do if your lemonade is too sugary? Well, you're going to add what? You'll add more water. And then if you're like, whoa, I added way too much water, then what are you going to do? Then you're going to come back and say, you know what? I need to add more sugar. All right. So you have a couple of words. We'll talk about what it means to be concentrated or diluted, but you can adjust how sugary your lemonade is by either adding more sugar if it's not sugarier enough, or if it's too sugary, you can add water and you can dilute the solution. And we're going to be talking about that. But the key word here is molarity, ladies and gentlemen. And molarity is given in the unit number of moles of solute, the salt, per liter of solution. All right, so we will move on and we will get to the crux of our lesson right now. So 2 things. We learned a long time ago that we have something called ionic compounds. An ionic compound is made up of a metal and a non-metal, and these things are ions. An ion, ladies and gentlemen, is a charged particle. A charged particle. And we talked about those, like you have sodium, and then you have sodium ion. You would have chlorine, and you'd have chloride or chlorine ion. And we talked about all these things where you had O2 minus, and we'd have Mg2 plus, right? Or potassium plus, or nitrogen 3 minus, nitride it's called. So we have all these different things. These are charged particles, and charged particles are called ions. And that's very important for us right now. Why? Because we've talked about this word soluble. And soluble means to be able to dissolve. Sugar and salt both dissolve, but now we're going to take it one step further. We're going to talk about something called disassociating or ionizing. You can see the word ion in the word ionize. And what that means is that when you take a salt or some type of ionic compound and put it in solution or make it pass into solution so it dissolves, it's going to form ions or charged particles. Again, that's called ionization or disassociation. I will use both of those words when describing this. Okay. And our homework today is going to be us working on practicing disassociation of ionic compounds. So we're going to try a couple right here. All right. So let's disassociate or ionize these things. So we're going to look back. I'm going to pull up my periodic table for you really fast. Now, we talked not too long ago when we practiced naming formulas and compounds, we had to figure out what the charges were. So we called those things ions. Just as a reminder, everything in column 1 is going to be a +1. Everything in column 2 is a +2. These are all +3s. These over here don't have a charge. Fluoride, chloride, bromide, those would all be -1s. Those would all be -2s. Nitrogens would be -3s, phosphide, all the way down until you got to that line, right? And so these would be the charges of these elements. And we talked about them before. So let's take a quick look. So let's Let's take a look at NaBr. So we're going to take NaBr, which is a salt. You know what? I'm going to change that. I don't want NaBr. I'm going to do NaCl because NaCl, it's so much more common. That's called table salt, right? We're going to take this NaCl, or this table salt, which is a solid. That's what the S means. So we're going to take this solid table salt and we're going to drop it into this container of water. If you ever see a container like this, it's water. What's going to happen is that the sodium and the chloride are going to break apart. It's going to break apart into Na plus, and it's going to break apart into Cl minus. There's always going to be a balanced charge in solutions. And we would write that as NaCl breaks apart or turns into Na plus plus Cl minus. Sorry, that's a Cl. Let me make that my cursive L, whatever. Okay, so this next one, this is a solid as well. We have potassium nitrate. I'm going to take that potassium nitrate and I'm going to break it up. We're going to put it into water. It's an ionic compound, and this one's going to break apart. And what will it break apart into? Well, we know potassium is in the first column, so it's going to be a +1 charge. And it also, we know that nitrate is going to be an altogether piece of equipment. Let me get that for you. I'm going to take you through this process. You're going to go to my resources. You're going to find the common ions. All right. And you're going to look through until you find NO3. And sure enough, NO3 is nitrate. It's one piece. It's one ion, right? Whoops. And that one ion is going to break apart into, this one here is going to break apart into K plus, because there's one K, and NO3 with a minus charge. So this will break up into K pluses and NO3 minuses. That's how this will disassociate, all right? Now let's move on. Let's do another one. This one, we have, oops, I didn't show you the last one there. Here we go. Whoops, let me do this. Go back, let me get us there. There we go. So what would I need to write here? I would have to write KNO3 solid breaks apart into, whoops, I didn't put a minus charge there, unless maybe deleted. A K plus, a potassium ion plus, an NO3 minus charge, okay? And let's move on down. So we're gonna break these up. All right, so let's take a look. We have to take calcium. We're gonna put this calcium fluoride solid. It's a solid. And we're gonna put that into the water. And this is gonna break up. Now, what do you think the charge is gonna be on the calcium? I'll let you know the calcium is right here. Yeah, that's right. It's gonna be a +2 charge. And each fluorine has what charge on it? Each one of those fluorines has what charge on it? That's right, each fluorine has a -1. And how many fluorides do I have? Yep, there's 2 fluorides right there. Well done. So when this goes into solution, it's gonna be a calcium, which is a 2+ charge. And it's gonna break apart into 2 fluorides. And you can see there's a 1- and another minus, which makes a 2- charge, and a 2+ charge, and those are gonna balance out. So we would write this, CaF2 yields calcium ion, calcium ion plus 2 fluorides. And that's how we would say 2 fluorides. And notice we have a balanced chemical equation. 1 calcium, 2 fluorides, 2 fluorides. We write it as a coefficient because there's 2 fluorides floating around. We do not, ladies and gentlemen, have an F2 in solution. These break apart into their own pieces. Do not, ladies and gentlemen, do that. That is bad. Bad. It's a no-no. All right, so let's take a look at this next one. A little more difficult, ladies and gentlemen. We have iron and we have sulfate. Now, you guys remember the charge on sulfate? Remember the charge on sulfate? Well, let's take, whoops, let's, oh my gosh, did I delete it? Where is it? Oh, no way I got rid of that. That's all right, we'll just pull it up again. Did I get rid of that? Must have. So there we have this one here. Pull that down so you can see it over here. There we go. And what we're gonna do, we have iron and sulfate. So let's find this SO4. So we find this SO4, we come over here to the sulfate side, and you can see this sulfate right here. You can see that sulfate is SO4 2 minus. So each one of these must have a 2 minus charge, because you're going, well, Mr. P, what's the charge on the iron? Well, we don't know what the charge is on the iron. Oh, I guess it's right here. I guess they went into each other. We don't know the charge on the iron because remember, these are transitionals. Remember these transitionals? These are transitionals. And that means we don't know what the charge is on them. We have to figure them out. Well, we know that the charge on sulfate is a 2 minus charge. All right, the charge on sulfate is a 2 minus charge, and we have 3 of them, right? So we have an SO4 with a 2 minus charge, an SO4 with a 2 minus charge, and an SO4 with a 2 minus charge. So this whole side equals a -6, which means that this whole side over here must equal a +6. So my question is, what's the charge on each one of those irons? There are 2 irons in solution. What is the charge on each one? That's right. Each one's going to have a 3+ charge because the charges have to balance out. A -6 balances out with a +6. I'm going to give you this. You're going to just draw arrows down, draw a little salt if you want to, and then you're going to show me how they break up in solution. At the very end, underneath it, you'll write Fe2, SO4 solid, breaks up into 2 iron 3+ charges plus 3 SO4 2 minuses. And that's what we have here. And this is a way of writing our balanced chemical equation. Some of us are struggling writing balanced chemical equations, but if you can just remember that you can look over on this sheet to help you out. H2PO4 with a 1 minus charge, PO4 with a 3 minus charge. And that's going to help you write out your equations and balance your charges. So your homework is going to be a bunch of examples just like that for you to fill out. All right, ladies and gentlemen, thank you so much. I hope that you understood today's lecture. Anything you don't understand, I suggest you go back and review. Okay, watch the video again. Have a great day. I'll be right here if you need anything.